Thank you everyone for joining. The next panel looks at case studies that were in the GIE in practice textbook. And we have three great presentations. We're going to start off with Sanchi Lokhande. She's a research associate at 3IE, and she's going to kick it off. Thank you.
Hi, everyone. Welcome to the last session of the day. Sorry to be the only thing standing between you all and cocktails. My name is Sanchi Lokhande, and I'm a research associate at 3IE. And today I'm going to talk about a geospatial synthetic difference and differences of an agricultural intensification program. A shout out to my co-authors, Fiona Castell, Devika Lakhote, Anka Dimitrescu, who is with 3IE, and then Douglas Glandon, who is with the GEI at the World Bank. Just a little bit of background on 3IE. 3IE stands for the International Initiative for Impact Evaluation. We're a non-for-profit research organization, and we generate and synthesize evidence and bring that evidence to policymakers, decision makers, and implementers so that they can make informed decisions on how to effectively transform the lives of the poor in low and middle income countries. We have supported over 300 impact evaluations in more than 50 countries, and you can read more about our work on our website or come find me later. I will begin by providing a little bit of context on the study region, although it may already be familiar to a lot of us. The study took place in Niger, which sort of sits at the heart of the Sahel region. We know the Sahel region as a semi-arid belt stretching across West Africa that is among one of the most climatically exposed regions on Earth. Two-thirds of the country is a desert, and nearly 75% of the country receives less than 300 millimeters of rainfall annually. What rainfall does arrive is concentrated in a single short season between June and October, highly variable from year to year, and increasingly disrupted by climate change. On the human dimension, 83% of the population lives in rural areas and is dependent almost entirely on agriculture and livestock for their livelihoods. These conditions sort of combined to make Niger one of the most food insecure and climate vulnerable countries in the world. And this in part informed the motivation for the kind of large scale irrigation investment that we evaluated. Oops. I don't think the animation is working well, but if you can see behind the text, the two regions within Niger that we looked at were Ibohuman and Dugurawa. There was a third region that was initially part of the study called Namaro, but was not included in this analysis because the implementation activities were still ongoing at the time of this evaluation. The intervention itself was called the Agricultural Production Intensification for Food Security in Niger, which was led by the West African Development Bank, or also called as the BOAD. Sorry about the really confusing French acronym. What exactly was the intervention? In response to a severe food crisis of 2008, BOAD initiated the Special Food Security Program to support countries' efforts to develop the region's agro-pastoral potential and boost agricultural production. The intervention itself was a bundle of activities which included building of dune fields, planting improved seeds, small shrubs, etc. But today we're going to be focusing on two irrigation perimeters that were constructed downstream of existing dams. A bit of institutional context that I think is interesting to share is that BOAD had a genuine interest in monitoring the construction of the irrigation perimeter, along with understanding whether the infrastructure they funded was working. The challenge, obviously, that they were facing, that we were all facing, was that monitoring and evaluation in this context is extremely difficult, owing to the remote location, security constraints, and limited ground data. I believe the implementation team was able to collect some amount of ground data in the beginning of the implementation, but this was happening at the time of an active coup in Niger, so they were unable to go back and collect more data. This institutional motivation is kind of part of what makes this collaboration interesting and part of why a geospatial approach was genuinely necessary in this scenario. The infrastructure in itself was completed in 2018, and I'm not sure if the animation is going to work, but there was a really cool animation from Planet Labs where we can kind of see from 2018 to 2023 the gradual evolution of the irrigation perimeter construction for Ibohuman. Prior to the project, these sites relied primarily on rain-fed agriculture, although some farmers may also have had limited access to existing dams and other naturally occurring water bodies, such as a nearby river. Agricultural production was largely confined to the single wet season cycle dominated by millet and sorghum. Feeder canals and water control gates were constructed to allow for allow for irrigation by gravity without pumping. And these perimeters were intended to enable dry season farming of high value crops, which included onions, tomatoes, etc., when there typically is no production. And then B, to enhance wet season yields of staples such as rice, maize, etc., by providing controlled water supply. So overall, the project kind of targeted two pathways, providing reliable access to water during the dry seasons, and then to enhance crop yields during the wet season through targeted water management interventions. The causal pathway that we were working with was that the surface irrigation infrastructure would allow for improved water availability and moisture retention, which would then lead to increased vegetation production and cropping intensity, which would then lead to enhanced food security and climate resilience in the long term. So beyond the operational challenge of limited field access, active conflict region, etc., there were some methodological challenges that we also grappled with. One of them was the non-random program placement. The intervention sites were selected based on proximity to existing dams with no formally documented selection criteria. We do not know precisely why these two sites were chosen over others, and hence comparability of control areas cannot be assumed in this case. We could not select controlled plots near other dams as the topography, soil type, waterfall characteristics may vary across sites. So proximity to a dam does not necessarily guarantee comparability. We also cannot choose plots closer to treatment area as there might be issues related to spillover. As we were mulling over what design choice to make, we systematically worked through the available quasi-experimental methods. And although all of these methods are really great, each presented a specific limitation in this context. I'll run through these fairly quickly. First on the list was matching. It selects sort of control pixels based on similarity in observable baseline characteristics. However, in this scenario, matching only balances those characteristics at a single point in time and does not account for time-varying shocks or unobserved heterogeneity. So for example, if there's a drought in 2005 that affects the control pixels differently from treated pixels, that would be an issue. We also considered regression discontinuity and spatial DID. Both designs rely on irrigation perimeter boundary as a source of identification. But as I mentioned before, that boundary was endogenously determined by program implementers based on proximity to existing dams. It cannot serve as a credible discontinuity or a spatial cutoff. Standard DID requires the parallel trends assumption to hold, given that the program placement itself was non-random. This assumption is difficult to maintain. And then synthetic control constructs a data-driven counterfactual, but does not include time-fixed effects, making it sensitive to common shocks. So for example, if in 2019, it was an unusually wet year everywhere, synthetic control cannot separate that from the irrigation effect in itself. It also performs poorly with a small number of treated units, which was the case in this scenario because we had to sort of do a lot of masking of some pixels because of cloud cover issues. So synthetic DID addressed all of these concerns simultaneously, and that was what led us to adopt it as our estimator. It combines the difference in differences with the data-driven weighting mechanism of synthetic control, constructing a credible counterfactual without requiring treated units and control units to be identical at baseline, as it matches on pre-trends. What you're looking at here in these panels is that weighting in practice. Each dot represents a control pixel within a 15-kilometer buffer. The color reflects the weights or how much each pixel contributes to the synthetic and counterfactual. Warmer colors are those whose pre-2018 vegetation and soil moisture trends most closely track the treated pixels. Gray pixels received zero weights. They were too dissimilar to contribute meaningfully to the counterfactual. We also see that the spatial distribution of weights differs between the two perimeters, reflecting the distinct agroecological conditions surrounding the two treatment sites. Our primary outcomes are NDVI and SAVI, both derived from Landsat 7 at a 30-meter resolution. Soil moisture from terraclimate serves as a secondary outcome, and we control for precipitation and temperature. A quick word on why we decided to use NDVI and SAVI both. There's some literature which says that SAVI performs better in regions where the vegetation cover is sparse because it corrects for the soil brightness factor, and NDVI sort of overestimates greenness in that scenario, which is the reason why we decided to use both of these in our analysis. A quick word on soil moisture also. At approximately 4,638 meter resolution, a single terraclimate pixel covers an area substantially larger than the irrigation perimeter themselves. This has direct implications for our soil moisture results, which I will return to when we discuss the findings, but this was the best data set available to us at that time. A quick shout out to the remote sensing inventory. It's a database that's created by 3IE because when we were starting out on this journey, we were also like not technical audience in terms of remote sensing and geospatial analysis. So we sort of combined all of our knowledge into that repository to be better able to understand how does NDVI differ from an EVI, from a GNDVI, or from a SAVI. To define our candidate control pool, we constructed a 15-kilometer buffer around the irrigation perimeters. Panel A is the 15-kilometer buffer, as we can see. The 15-kilometer is a bit arbitrary number, but it sort of balances computational feasibility with ecological comparability. We also did a visual inspection in Google Earth Engine to confirm that the buffer region includes natural water bodies and landscape features comparable to the treated area. One question that naturally arises is whether the 15-kilometer buffer threshold in itself influences the results. To address this, we re-estimated the control pool at 15 to 20 kilometer in panel B, and then 20 to 25 kilometer in panel C. This serves two distinct purposes. First, to reduce the potential spillover contamination from pixels immediately surrounding the perimeters, and second, to test whether the results are sensitive to buffer specification. Results remain consistent across all three panels, strengthening confidence in our primary estimates. I'm gonna skip over the estimation framework, but just wanted to note that we control for pixel fixed effects and time fixed effects in the specification. Going to our main results, these panels show the pooled average treatment effects pooled from both the irrigation perimeters on vegetation and soil moisture. NDVI and SAVI, as seen in panel B and C, increased substantially by 43% and 39% over baseline. This divergence kind of can be seen very clearly in these panels. In panel A, we see that soil moisture shows no statistically significant effect. Treated and controlled pixels continue to track each other after 2018 with no meaningful divergence. This finding is reflective of the resolution problem that I discussed earlier. The resolution is too coarse to detect canal scale changes, which explains the null results. Another interesting finding is the heterogeneity in results by region. Ibohuman shows an NDVI increase of approximately 80% over baseline. Dugaroa, on the other hand, shows a much smaller increase of approximately 10% over baseline. Both results are statistically significant, but the seven-fold difference in magnitude is a substantive finding. We observe the same pattern across soil moisture in column, soil moisture in column 1 and 4, although soil moisture overall was not statistically significant. Methodologically, it demonstrates that the pool estimate in the previous slide was masking meaningful spatial variation in program effectiveness across these two sites. We hypothesize that this heterogeneity is due to the implementation quality, farmer uptake, and local conditions as plausible drivers. The two main policy implications that stand out are that small-scale irrigation can substantially enhance agricultural productivity in these semi-arid contexts. That is an important evidence contribution in a region where irrigation investment decisions are often made without rigorous impact data because of how difficult it is to get this data on ground. Spatial heterogeneity in program effectiveness also suggests infrastructure alone does not guarantee productivity gains. And I think this was one of the findings by Kunwar in one of the sessions yesterday. So sustained maintenance, governance, and complementary inputs also influence the realized impacts. Three limitations worth flagging briefly. First, the coarse resolution of terraclimate soil moisture data, which we have already discussed. This issue can be solved by using now a high resolution imagery that is available or an ML-based downscaling. Second, our intent to treat design captures infrastructure access rather than actual farmer adoption. So our estimates likely understate the effect of farmers who actively irrigated. This can be partially resolved through ML-based land use classification to identify actively cultivated pixels within the perimeter. Third, multiple simultaneous interventions such as land rehabilitation, watershed management, and soil and water conservation within this program, but also because of other programs in the region, mean that we cannot fully isolate the effects of irrigation alone. On the computational side, the scale of pixel level data creates constraints. The 15-kilometer buffer is a huge region, and we sort of had to gather pixels from all of that region. So it's computationally super heavy. And spatial autocorrelation between neighboring pixels complicates standard error estimation, though we addressed this through these robustness checks that we did. Tying the limitations to the previous slide, since then newer AI and machine learning methods have evolved, and our team has been applying these across several country contexts, as we can see here. That was all from me. Thank you so much.
Thank you very much. We'll hold the questions until the end, so if you have any, please just write them down. Our next presentation is from Foster Mensah. He's the Executive Director at the Center for Remote Sensing and Geographic Information Services at the University of Ghana.
Yeah. Okay. Yeah, so thank you very much for this. I must say that I'm doing this on behalf of my entire remote sensing team at the Center for Remote Sensing and Geographic Information Services. We are based in the University of Ghana. And this case study, which is in the chapter 30 of the book, was motivated by the intense illegal mining activities in Ghana. And the objective is to develop a workflow that estimates the causal impact of mining on deforestation. And so we have been doing this together with the team for a very, I would say, sizable but small area within the forest belt in Ghana. And so we would say that Ghana has lost just about 2% of forest cover annually from 2015 to 2023 due to other drivers, including small-scale mining. The small-scale mining activity has expanded along major river corridors and forest ecosystems from 2015 and onwards. And so, like I said, the question is how much forest loss can we attribute specifically to mining after controlling for the other external factors. And why did we decide to do this, and why now? Because this case study area is within the high biodiversity hotspot within, as you can see, the fragmented forest reserves within the forest zone. And given that gold, the production of gold has surged over the years, especially, and also Ghana becoming one of Africa's largest gold producers, the output, especially from small-scale illegal mining, has increased sharply. Fortunately for us, data availability has been quite good. We are able to assess the NICFI planet imagery, which is high resolution, and as well as the Hansen's global forest change 30-meter data, which provides good quality geospatial data and also spatial coverage over the area. But the most important thing is that we want to be able to provide some evidence-based output that will help drive policy. We know the government has unsuccessfully tried to halt illegal mining activities in Ghana. And the idea is to specifically estimate how much mining specifically has been contributing to the deforestation in the region. And so the GIE framework that we looked at was the difference in differences. And the idea was to take the illegal mining footprints that we have been working on over the years, because we had, as part of the USAID severe program, we had been mapping the extent of illegal mining footprints and making that available to the government agencies. And the next step was for us how we can link this to deforestation, but then we have to also look at the causal impact of that, not only where what is, but also the driver and the specific contribution of that driver to deforestation. So this was the framework that we used. And like I said, fortunately, the data sources, we have credible data, we have open data from the NICFI data through the Hansen Global Forest Change data, the SRTM data provided us also some of their covariates. We also were fortunate to have some data from the Ghana Lands Commission, the road network, and also the river network has been mapped, and the digital versions are available. And so, yeah, so data sources were not a problem for this case study. And so, as you can see, that's the spatial resolution, the temporal coverage, and then the sources of the data. I must say the whole area was tessellated into 1 kilometer by 1 kilometer grid and superimposed over the steady 305 out of the 3,900 total 1 kilometer by 1 kilometer grid. But to account also for spillover effects, we applied a 3 kilometer buffer and excluded any pixel that was within the control pool to prevent contamination. And then prior to the difference in difference estimation, we matched the treated and the control. We used these 5 covariates, but I'll get to that in a minute. And then subsequently, we estimated the causal impact. And so for the matching, these are the covariates that we used from elevation, which we derived from SRTM slope, road proximity, river proximity, and then the baseline forest cover, which we got from the Hansen's global forest change data. So this was basically what we came up with. The details are in chapter 30 of the book. We have all the details, and as part of the workflow, we also developed a GIS workflow that can be replicable by other practitioners or other people that would want to follow the same process. So this is the estimation from the difference in differences. And so as you can see, the contribution of 1.4 percentage points extra forest loss, which was attributable to mining, which means that about 18% increase above the counterfactual rate, and these were statistically significant. We did a robust check, used the regression adjusted, and then the propensity score matching, and that were the estimates that we got in terms of in percentage points above the counterfactual. Eventually, we decided to settle on the conservative primary estimate using the CEM because that was where we were able to match the control pool and also the treated pool. But for robustness checking, we looked at the regression adjusted DID and then the propensity score. And so our key finding is that about 18% of the forest cover loss would be attributed to mining averagely within that steady area. Given that we also were able to use these other robustness checks, we found out that all the three specifications confirmed the direction and significance, and so we thought that we would settle on the most conservative finding of 1.4 percentage points above the counterfactual. Now, we found out also that for our policymakers, we would be able to say to them that the high impact areas were within river corridors where the highest treatment effect cluster around river channels and tributaries due to access to water for cleaning the debris and also extracting the gold. Partial in forest reserve, we would say that even though formal protection is available, we found out that there were some incursions into the forest reserves, and these have been documented. Roads adjacent to those corridors also had elevated losses, especially near the existing roads because of the accessibility to the sites. This area is in the highlands, and so in the most remote places in the highlands, that was where there was lower treatment, which is obvious because these are very remote areas and difficult to assess. And finally, what does this mean for policy? We are saying that the river corridor and road adjacent cells show highest mining attributable loss. And the impact evaluation output maps provide enforcement agencies with spatial priority rankings to enable resource allocation where it has the greatest impact. For the forest reserve boundaries, as I mentioned, we will caution that the protection and enforcement would probably have to be a little bit more strengthened because of the incursions that the miners, the illegal mining operators are able to move into these forest reserves. Like I said, even though there are so many drivers of deforestation in the landscape, we are beginning to see the significant impact of mining as a very distinct driver of deforestation in the region. And I think, like I said, the idea is to be able to replicate this and probably scale it to cover other areas. Well, thank you very much for your attention.
Thank you very much. Our next presenter is Boyan Ha. She is a PhD candidate at ETH Zurich, and she is working on national disaster impact.
So I would like to say thank you again for this opportunity, and thank you everyone for participating today, and I will try not to keep you for long. I'm going to talk about the book chapter on measuring the local economic impacts of typhoons. And this is the work done with my co-author, Kenneth, sitting over there, Etienne Espan from the French Development Agency, and Thanh Ngô Đức from USTH University in Vietnam. So we'll go through context and then what has been done in the literature. Then we talk about how we do things, and then we present the result and show some discussion. So in terms of context, global damages from natural disaster have increased markedly. It's not only because of climate change, but also because of the growing concentration of population and of economic activity in hazard-prone regions. And tropical cyclone is one of the most destructive natural disaster. So understanding how local economies respond to these shocks is very essential. It helps identify vulnerable regions, but also to inform effective disaster risk management and adaptation strategies. So we look into Vietnam, which provides a very interesting context. The country is located in one of the most tropical cyclone active region in the world. It also has extensive coastline, and every year there's around 5 to 6 tropical cyclones making landfall. More interestingly, economic activity in the country is unevenly distributed. In the north, you have the Red River Delta, and in the south, you have the Mekong Delta, which host industrial hubs, very densely populated, and big urban centers such as Hanoi, the capital of Vietnam, and but also extensive agricultural production. Meanwhile, the center of Vietnam is predominantly rural and sparsely populated. So it gives us an ideal context for a hands-on geospatial impact evaluation, because we can measure the impact of typhoons in different regions with varying degree of economic development and built-in resilience. So tropical cyclones are interesting phenomena. They're bad, but they're also interesting. And they pose a very specific economic shocks. They come with strong winds, heavy rainfall, storm surges, and they cause like prolonged floodings. They destroy physical capital and sometimes cause temporary displacement of labor, which further cause subsequent disruption of economic activities. And also post-storm responses such as emergency relief or reconstruction effort can further influence what we observe afterwards. At first, they seem like they're exogenous because you don't know exactly when or where they would hit, only up to a few days in advance. But in the long run, they are not randomly distributed, because if you're located at the coast, then you're more likely to be affected as well. So measuring the economic impact of tropical cyclones is complicated, because you cannot simply just compare never affected with frequently affected, because due to the different resilience, you may bias the estimates. So The literature has looked into tropical cyclones' impact in Vietnam specifically at the household level and at the firm level analysis, but they will provide very limited insights, especially related to how persistent the effects can be. So mostly because of the lack of good data, they are costly and infrequent. And also because they use ex post damage or self-reported exposure to identify where has been affected by typhoons, and these comes with their bias and measurement errors. This is where Earth observations comes in. So we can use storm track archives with physical attributes, with temporal and spatial resolution, and we can create our own administrative level exposure metrics. Then we also have satellite-derived nighttime light, which has been shown to be a good proxy for economic activity at good geographical resolution, but also over a long period. And this is especially relevant in the case of Vietnam, where we don't even have subnational GDP. Then in terms of causal identification, as I've said, is quite complicated because storms can come and go. It can happen this year and not the next. And the exposure vary across space and time. But thanks to the recent econometrics development, all these difference estimator, now we're using the work done by the Martin and Dufoy. I hope my French is correct. And it is a very powerful tool. You can see exactly which units, which events are included in the estimates. And all these advancement underlines the new generation of geospatial impact evaluations. We're in an exciting era. So in the book chapter, we present a reproducible step-by-step geospatial framework for estimating the local economic impact of typhoons. So first, we integrate the storm track data with the satellite-derived nighttime light at the administrative level 1 of Vietnam, which is called province. And by doing this, the analysis aligns exposure and also outcome at the level where policy decisions are implemented. From the data extracted, then we construct a panel dataset of province year, typhoon exposure, and nighttime light intensity. Then we apply the difference in difference to estimate the dynamic effect under staggered exposure. So now I'm going to go deeper into how we construct each variable. So with the typhoon exposure, we use the International Best Track Archive for Climate Stewardship. It's basically compile the storm tracks from different meteorological agencies around the world. You have the 6 hourly coordinates of the storm centers and the associated physical features. We focus on a very strong storm only, more particularly typhoon level. And we also know the 30-knot wind radius, which is the radius around the storm center that we know would experience wind speeds of at least 30 knots. And we overlay the wind radius over the administrative boundaries, and we can compute the land area exposed to wind speed exceeding 30 knots. And our treatment variable in this case is an indicator that takes value 1 when a province has a strictly positive exposed land area. Now we use nighttime light as our proxy for economic activity. As you can see in 2000, the brightest area concentrate into economic hubs of Vietnam, which is Hanoi in the north and Ho Chi Minh City in the south. And over the year, these economic hubs become brighter and also expand. So there are 2 original nighttime light composites. First is DMSP, starting from 1992 at around 1 kilometer square resolution. The measurement unit is digital number. there are also known limits to this series. So, for example, saturation, it means that they cannot look further than 63 digital number. They're top coded. And also blooming, which refers to the case where very bright area, the light would stray into the darker areas. And then there's also consistency between sensors because they lack onboard calibration among different satellites. And also as the satellite degrade, so within one sensor, they would have measurement inconsistency as well. And then the next generation is the VIRS, available from 2013 with better resolution, but they have different measurement unit. There have been efforts to harmonize the two data to create one long data. So for example, the series by GeoField et al. So first they adjusted the DMSP series, so they calibrate across different sensor, and they also correct for the problems, the saturation and the blooming. And then since the two resolution is different, so they have to downgrade the VIRS to match the DMSP, so around 1 kilometer resolution. And then they use the ensemble method to harmonize the two series. So we download all the data at the provincial level by averaging the nighttime light intensity of all the pixels located within the same administrative boundaries. So in terms of methodology, we use the difference in difference framework, and we have the common identifying assumptions, no anticipation, parallel trends, which are partially testable by looking at the pre-exposure period and also SUTVA. So essentially, we compare changes in nighttime light intensity before and after exposure in affected provinces with provinces that have not yet experienced typhoon. And it is implicitly assumed that because we start our data sets in 1992, so it's implicitly assumed that the storms before 1992 do not affect nighttime light after 1992. So these are the results, and the year 0 in this graph represents the benchmark period, the period when the typhoon happened, and this is the result using the harmonized nighttime light series. So the pre-exposure coefficients are expected to remain close to 0 to satisfy the parallel trends assumption. And the result shows a decline in nighttime light intensity following typhoon exposure, which indicates a negative impact on economic activity up to 3 years after a province experienced typhoon. And then we also just simply merged the two DMSP and VIRS dataset. The estimated effects are broadly consistent, but the negative effects only last up to 2 years after typhoon exposure. Now, this chapter is simple, and it presents a reproducible step-by-step geospatial framework by estimating the local impact of typhoons. So we beyond our contribution, the application in Vietnam, we contribute in 3 key ways. So we demonstrate how harmonized nighttime light dataset can support longitudinal analysis across multiple satellite systems while also preserving their temporal consistency. And we also apply the most recent econometric advances to estimate the dynamic treatment effects under staggered exposure. And we provide a transparent and transferable workflow that can be adapted to any other country and hazard context where geospatial data are available. This chapter bridges geospatial measurement and causal inference, offering a policy relevant and hands-on template for disaster impact evaluation. we also learn a lot from this. So first, our exposure definition is very restrictive. So typhoon province is considered affected by typhoon if any share of area being exposed. And it means that intensively impact and minorly impact are similar, treated similarly. And if you want to have varying intensity, then you can try different measurement, such as wind speed or the portion of land being affected. And also, since Vietnam is frequently exposed to typhoons, the repeated typhoon exposure complicates the interpretation of dynamic effects. We see an adverse effect, but it could be due to slow reconstruction effort, cumulative damage, or it could be because that province experienced another typhoon right away after having been exposed. And similarly, the biggest assumption is that storm before 1992 do not affect the nighttime light intensity of provinces. And this require much more careful plausible tests and sample selection to further strengthen identification. And and then the third lesson, as we saw that using different nighttime light data sets slightly change the results. So any analyst should consider the trade-offs between temporal coverage or spatial resolution or sensitivity to economic shocks. Thank you.
Thank you very much. Thank you all. I would like to take any questions. It's good.
Super interesting, all of you. Thank you. My question is for Foster. You mentioned that one of your priorities is the transferability of the methodology to local agencies, and I'm wondering what platform are you using? Is that Google Earth Engine or something else? And have you had success with other agencies that aren't involved in the project replicating the methods? If so, I have tons of follow-up questions for you later. And then I'm wondering how you're planning to deal with the lack of NIC data going forward.
Yes, thank you for the question. We are using ArcGIS as the main platform, even though we tested some of the, especially the illegal mining footprints with Google Earth Engine. But for this workflow, because of the intensive geospatial part, we are using ArcGIS, which can also do a little bit of image processing. But basically, we use ArcGIS for it. For NICFI, right now for NGOs and nonprofit organizations, and sometimes even for government agencies, the NICFI data is still available. For us, for instance, for research and also for some nonprofit activities, and for activities like this, it is still available. And so we can access the NICFI mosaic, the tropical mosaic data. And what other question did you? No. Yeah, okay, thanks.
I have some questions then. So my first question was for Sanchi. When you presented the synthetic DID, you presented it as kind of, we went through all these other things and this was the last resort. So what are some cases where it might be like, we can think of it as the first option, as a really good option?
but this was not the first option because this was it's kind of like a new method. So we kind of went down the rabbit hole of trying all of these other options and considering whether they would be a good fit. But we eventually landed on synthetic difference in difference.
My question is for Boyan. Sorry if you said it and I missed it, but did you control for any other variables? Like, did you do any matching in your comparison?
No, we use the simplest form of difference and difference.
Yeah.
Yeah, so we don't control for any variable. Also because there's not very good data in Vietnam at the subnational level that you can control.
Yeah. I was just thinking because you're averaging nightlights over quite a large area. So I was wondering if like the fact that some provinces are more rural than others could kind of complicate the estimation of the impact of typhoons.
So I think if you average, then the rural area tend to be very vast and not very well lit. So their fluctuation in nighttime light intensity is smaller. So when they're aggregated into the estimate impact, it can be drowned out. So that's the only problem I see. If that answers your question.
One other tiny question. You also probably said this and I missed it, so sorry.
Probably.
But was your treatment indicator binary? Or
yes, binary.
Whether any part of the province was affected by the typhoon or not?
Yes. Yeah, any share. So that's why we also say that it's a very restrictive measurement because we see the big portion of land being affected as the same as tiny portion of land, and depends on where they're located. Different portion may be affected intensely and some are not so intensely, but it's very complicated. But in this chapter, we try to make it as simple as possible.
Yeah, I guess you could say that even if only 5% was affected by 30 knot winds, a large area will be affected by high winds, just not the 30 knots, isn't it? So that's okay.
So I think if you measure that only 5% experience 30 knot wind, it means that 30 knot and above.
Yeah.
So the rest would not be affected.
No, but they would also have high winds, just not the 30 knots, because it's not like a discrete. Yeah. Cool, thank you.
Thank you.
Yes, very interesting study. I've been living in the Philippines for more than 15 years, and I've also witnessed many typhoons, same as in Vietnam. The worst you can possibly imagine. And when I saw your study, I was very fascinated. To what extent this can be replicated on a country like the Philippines? When you look at it, we always claim in the Philippines that the typhoon hits the Philippines first and then it goes to Vietnam.
Yeah.
So, yeah. So I was very fascinated. So you have to start the Philippines first before you get there. So how much data, requirement is needed to replicate something like this on a country like the Philippines? The people will be very interesting to see those impactors.
So this framework can be reproducible to any country, and I think you just need to download the data from Google Earth Engine. And in the book chapter, you can just click on the link and you can already download. Maybe you just change the boundaries you want. And you can definitely apply to the Philippines, but the Philippines are even more affected by typhoons. Yeah. It's so frequent. Yeah, it's like the shield of other countries.
Yeah.
So maybe you don't get to measure as many events because you have like so many affected provinces.
Yeah, thank you. I would definitely be interested in that. Second question, most of these countries are also, there's a early warning system. Mm-hmm. We usually get a warning like 2 weeks ahead of a typhoon. So we get prepared somehow.
Yeah.
To what extent this has also impacted the effect that you see on economic activities?
So our measurement of nighttime light is an annual average, right? So the early warning system you can prepare only for a few days, or so I don't think it would change dramatically the results. Yeah. Also because you cannot move economic activities that fast.
Yeah.
Thanks.
Question for Foster. Are most of these illegal gold mining operations located around like the Anglo Gold Ashanti larger mines, or are they dispersed away from the mines?
Yeah, they are dispersed, but these, like I said, these are along the main river channels, but they are all over the place. And, if you looked at Ghana on Google Earth, you just see the forest belt is here.